In these slides, we want to study the charging process of a capacitor. So we put a capacitor that's uncharged in a circuit with a battery, a switch, and a resistor. And at time less than 0, the capacitor is uncharged and the switch is open. So what do you think will happen when the switch is closed? An electric field will be established in the circuit, and what would that electric field do? The electric field goes from the positive to the negative plate. What do you think the electric field would do to the charge on the capacitor, or would it want to do? So of course we're taking the case where the wires are very close to ideal wires, so the electric field is very weak inside the wires and the resistance is very small amount of resistance. So we can neglect any potential drops across the wires themselves. So all the potential drops are across the capacitor, battery, and the resistance. So because of the electric field here is going upwards. That means the negative charges in the wire, they want to go opposite the electric field and onto this plate. So this plate wants to become negatively charged. And then you have here already this plate is neutral and there's an electric field pointing towards the plate. So that means the negative charges will want to go off the plate and into the wire. So this plate will start to become positive later on. Right now we're looking at the time 0 plus. 0 plus is just after you close the switch. So still no charge has accumulated on this plate and no charge has left this plate yet. It will leave and accumulate at a later time, but so far at time 0 plus, still no charge has accumulated on the plates. The current in the circuit has a value I naught, and it goes in the direction of the electric field, in this direction. And so we want to see at this point in time, when you just close the switch, what's the loop equation? So the loop equation, if you start out, for instance, over here, and you go from here to here, the potential increases by epsilon. And then when you go from here to here, there's no potential drop across the capacitor because it's not charged yet. And then when you go from here to here, the potential decreases by a factor of I naught times R. So you get minus I naught times R. And then we reach the same point we started from. So the loop equation, you set that equal to 0. So this will be the loop equation at the initial point in time when you close the switch. You can reverse this to get I naught in terms of the EMF of the battery and the resistance. So this is the initial current in the circuit. Now notice that at this initial time, the capacitor acts like a short circuit. It's as if it doesn't exist. It's as if this is just a wire. There was no potential drop across it. Okay, now if you wait for a little bit more time, some time bigger than 0 in general, any time, you would have had enough time for the charge to accumulate onto the top plate, the negative charge, and enough time for the charge on the bottom plate to leave, so this becomes positively charged. But still, this is not the maximum charge that the capacitor will reach. It's some intermediate value. That's why I put it small q. And the current in the circuit will not be I naught, because I naught was the initial current. No, it's just some general current at that time t. And so we want to see what is the loop equation at this point in time. So again, if you go around the circuit, you go from here to here, the potential increases by epsilon. You go from here to here, the potential decreases by a factor of Q over C. You know the relationship between capacitance, charge, and potential difference across a capacitor. The potential difference is Q over C, but the potential here is lower because the electric field between the plates goes from the positive to the negative plate. So the electric field goes from high potential to low potential. So this point is at a lower potential than this one by an amount Q over C. So that's why you have the minus Q over C. And then when you go from here to here, the potential decreases by a factor of I times R. And then you've reached back to the same point you started from. So this will be your loop equation. You set it to equal to 0. Okay, what about when you wait for a very long time? Time goes to infinity. Well, when time goes to infinity, the charge will, the maximum charge will have accumulated on the capacitor plates. This will be minus big Q and plus big Q. And the current in the circuit will go to 0. And everything will just stop. And that will be the final situation where you have the capacitor with fully charged and the current goes to 0. What is the loop equation in this point in time? So again, go from here to here. The potential increases by epsilon. When you go from here to here, It decreases like before with a value minus Q over C. But then when you go from here to here, there's no potential drop across the resistor, because when time goes to infinity, the current becomes zero. So you reach back the same position you started from, and you equate that to zero, and you get that the maximum charge that the capacitor will reach is just the EMF of the battery times the capacitance. So notice that the capacitor behaves in a different way than at very long times. At very long time, the capacitor behaves like an open circuit. So the current cannot pass through, and the current just goes to zero at very long times. So what do you think a sketch of the current and charge would look like as a function of time? The charge gets bigger and bigger as time goes on, and then it reaches a maximum value. The current starts out maximum and then decreases. Expect this kind of behavior. Charge starts out at zero, and then it will reach some maximum asymptotic values at infinity, and then the current starts out at maximum value and reaches zero at t equal to infinity. And the way to get then the exact value of the charge as a function of time and the current as a function of time is by looking at the differential equation that we wrote down for the intermediate time, when the charge was small q and minus q. This was the loop equation, and the current here we can write it as dq by dt. So if we substitute here I as dq by dt, you get a differential equation. The differential equation has a certain solution, but it's not enough to give the differential equation. You need to give an initial condition. You need to give a certain condition that you're using for your particular problem. In this particular problem, when the time was zero, the charge on the capacitor was zero. So this initial condition is needed in addition to this equation to give you the unique answer for this particular problem. Notice if you have, for instance, a differential equation dy by dx equal to 1, how many solutions are there for this equation dy by dx equal to 1? There are an infinite number of solutions. So to pick out the solution that you want, you need to specify something that will pick out only one solution. So this condition is needed for that. And we'll see during the derivation, we'll do the derivation later in a different file, how this condition is used to get the unique solution to this particular problem. So we're going to show again later on, not in this file, but in a separate file, how to solve this differential equation with this initial condition, and this is what the solution would be. Charge as a function of time is equal to the maximum charge times 1 minus e to the minus t over rc. The current, when you take the derivative of the charge with respect to time, you get I node, where I node is this value, e to the minus t over rc. Let's see if these have the typical quality that we expect for the charge and the current. If you put q at time 0, what's e to the power 0? 1. So you get 1 minus 1 is 0. So this works out fine. The charge at time 0 is 0. Now when you put time equal to infinity, t equal to infinity, e to the minus infinity is 0, so you get q. So this gives you the correct asymptotic values for the charge. And then let's look at the current. When you put time 0, e to the power 0 is 1, so you get I node, which is the value we got before correctly. So and when you put time equal to infinity, e to the minus infinity is 0, so you get 0. So this gives the correct behavior that we expect, and these are the equations then for the charge and the current as a function of time for the charging process.